Okay, today's lecture we'll call 5.4b, and instead of taking derivatives of exponential functions, we're going to integrate exponential functions. Alright, so integrating exponential functions almost always involves u substitution. So if the derivative of e to the x is just e to the x, then if you integrate e to the x dx, that's also just going to be e to the x. Alright, so let's just do a few examples. Our first one is let's integrate e to the 3x plus 1 dx. Alright, if we can make this e to the u du, then the antiderivative of that is just e to the u. So let's let u be 3x plus 1. Du then would be 3 dx. So 1/3 du is going to be dx. So then we could rewrite this as 1/3 e to the u du. Alright, so that's going to be 1/3. The antiderivative of e to the u is just e to the u, so 1/3 e to the u plus c. So we need to substitute u back in, so that's going to be 1/3 e to the 3x plus 1 plus c. And then you can take the derivative of that, and if you do, to check it, then you'll just be back right at e to the 3x plus 1. Alright, the next example is let's integrate 10x to the 4th plus 4x times e to the x to the 5th plus x squared minus 1 power dx. So you want to pick a u when you take the derivative of it, it's sitting out in the problem. So, and that's usually the exponent. So let's let u be x to the 5th plus x squared minus 1. Then du would be 5x to the 4th plus 2x dx. And that's almost what we need. We need 10x to the 4th plus 4x. So if I just multiply this by 2, each side by 2, we'd have 2 du is equal to 10x to the 4th plus 4x dx. So now I can rewrite this integral in terms of u. Put that 2 out front, and then we would have e to the u du. Right, since du is just 10x to the 4th plus 4x, that's that, times dx, that's that. So we would have 2 e to the u plus c. So that's going to be 2 e to the x to the 5th plus x squared minus 1 plus c. And if you take the derivative of that, you will end up right back here to check it. go to the book, let's look at example number 76 on page 346. That is e to the minus x to the fourth times negative 4x cubed dx. This is a really straightforward one. If we let u be minus x to the fourth, then du is going to be minus 4x cubed. And so u is minus x to the fourth. Du would be minus 4x cubed dx. And now we can rewrite this as just e to the u du. And that's going to be e to the u plus c. Substituting u back in, we would have e to the minus x to the fourth plus c. All right, so that one was a really straightforward one. Okay, we'll throw a few more interesting problems in the mix. The next example is number 80 on page 346. And for that one we have e to the 2x divided by 1 plus e to the 2x dx. Now remember, we don't want du to end up on bottom. So I'm going to pick for u the bottom of the fraction. Okay, so we'll let u be 1 plus e to the 2x. So du is going to be e to the 2x, but then we have to multiply by the derivative of what we call the blob. So multiply by 2, the derivative of the exponent, and then dx. Well, that's almost what we want. We just want e to the 2x dx, so I can multiply both sides by a half. And now we can rewrite this integral in terms of u. So we have 1/2, and then we'll have on top du, and on the bottom we would have u. Du e to the 2x dx, that's on top, and on bottom u. Now this is, of course you'll remember from earlier, section 5.2, this is going to be natural log. So this will be 1/2 times the natural log of the absolute value of u plus c. So that's 1/2 times the natural log of the absolute value of 1 plus e to the 2x plus c. You take the derivative of that, and you would end up right back here. All right, next example is number 88. In this one we want to integrate e to the 2x plus 2e to the x plus 1 over e to the x. Now this is one where you really don't want to enter into u substitution, because since you only have one thing in the denominator, you can divide that into each component of the numerator and simplify this and end up just using the power rule for integration. So rewriting this, e to the x will go into e to the 2x, just e to the x times. E to the x will go into 2e to the x. The e to the x is canceled, so plus 2. And then 1 over e to the x, we can rewrite that as e to the minus x. All right, now I'm just going to integrate each section one at a time. So the antiderivative of e to the x is just e to the x. The antiderivative of 2 would just be plus 2x. And then the antiderivative of e to the minus x, I'm going to hold off on the sign here. We know it's going to be e to the minus x, but when I take the derivative, I'm going to, in order to get back to this, I take the derivative, I'm going to need a minus out front here. Because this would be e to the minus x times negative 1. So minus minus would make a plus. So then plus c. So this problem, the purpose of this example was to get you to rewrite it so that you don't even have to use a u substitution. All right, I have one more example, and then this lecture will be finished. Number 90. And we're going to involve a little trigonometry here. So we have e to the tangent 2x times secant squared 2x dx. All right, we know that the derivative of tangent is secant squared. So since the derivative is sitting out to the right out in the problem, we'll let u be tangent 2x. Then du is going to be secant squared 2x times the derivative of the angle or the block, so times 2. And dx. Now, that's almost what we need. We don't want the 2 out front, so I'll multiply both sides by a half. All right, so we have 1/2 and then e to the u du. So that's a real simple integration. That's going to be 1/2 e to the u plus c. And now we can just simply put u back in the problem. We would have 1/2 e to the tangent 2x plus c. All right, the homework for this section is on page 346, and it is 75 through 91 odd. And that concludes 5.4b AP Calculus lecture.